جابوا يعني method how to find that the system is stable without solving the characteristic equation. So if you remember, we usually we write the transfer function g of s. Now we write it in this form: g of s is equal to numerator of s over denominator of s, numerator and denominator. And usually we call this one ds. Usually if we have just one unity feedback, if this is g of s, and this is the output c of s, and you are taking a feedback h of s. So here we have the feedback, and then here we have our desired input, which is r of s. So negative, positive, and then this is. So in a characteristic equation, the characteristic equation is written in this form: 1 plus gs h of s, which can be written like this. In general, c of s over r of s can be written in this form: j over 1 plus js h of s, js h of s. Usually we call 1 plus js h of s the characteristic equation. This is known as the characteristic. Here, it's the characteristic polynomial. But when we equate it to 0, 1 plus js h of s is equal to 0, we call it characteristic equation is equal to 0. Suppose this transfer function is written in this form. Suppose our transfer function is written h of s as the transfer function, the closed loop transfer function is written in this form: 1 over s plus a, 1 over s plus a. Okay, we assume here that a is positive. A is positive. What is the pole here, Shabab? The pole is s is equal to minus a, and in the imaginary axis, or in the imaginary plane, so this is the real, this is the imaginary plane, so s is equal to minus a is here. Now, if you take Shabab Hina, if you take this, if you take the inverse Laplace transform, you will have the inverse Laplace transform, it will be a to the minus at, a to the minus 80. This is the inverse Laplace transform, it will be a to the minus 80. So a to the minus 80 will be something like this. Simply with time, it will go to the 0, or to the, it will be converging to 0. So this is f of t, and this is exponential minus t, minus at, it is converging. Now see the situation when we have this function 1 over s minus a. The transfer function now is 1 over minus s minus a. What will happen, Shabab? Can anybody tell me what will happen? If we have f of s is equal to 1 over s minus a. So what will be f of t? Will be equal to what? F of t will be equal to a to the power 80. A to the power 80, it's increasing with time. Increasing with time. So it could be something like this. So we say that our function here, it's not stable. Not stable. Why? Because it's increasing with time. Not like the previous one. When the poles lie here, s is equal to a, s is equal to plus a, the pole is lying on the right-hand side plane, and this one will be like this. S is equal to a will be here. So here we decide whether the pole lie on the left-hand side plane or the right-hand side plane is like this. So we wrote the characteristic equation in this form, and we have this is the h of s is equal to 1 over s plus a. If a is positive, so s will be negative, will be here on this point. If a is negative, so s will be positive, and it will be here. So this guy, the left-hand side, will be e to the minus Laplace transform inverse. It will be exponential minus at, or simply exponential st, which is here. decaying. Decaying when A is positive. When A is negative, this one, it will go here, and then it will be unstable. So we don't care about A is equal to 0. We don't care about 8 is equal to 0 because it will be like this. It will be just step function. We have seen this one. A is equal to 0 is not a case of study because it's step function, it's constant. So, Shabab, we have another example here. If we have 3 poles, مثلا, 3 poles, H of S is equal to 1 over S plus A, 1 over S plus 3, 1 over S minus 2. It can be written like this using the partial fraction A over S plus 1, B over S plus 3, C over S minus 2. So if you take the inverse Laplace transform of this, the first one will be e to the minus at, e to the minus at, it will be decaying. B exponential minus 3t, it will be decaying. C exponential 2t, it will be increasing with time. So here, Shabab, the pole to be, the system to be stable, it has to have the poles in the left-hand side plane. So the poles must lie here in the left-hand side plane. If the pole lies here, so the system will be unstable. This is the basic idea, and this is the main idea of stability. So this is what we have here now. This is a stable system. You can look at it like this for this cone. When it is placed on a horizontal surface, this is a place when it is stable. This is when we can neutrally stable, and this is when it is non-stable. As the location of the poles, here, when the poles lie on the left-hand side plane, the system is said to be stable. When the poles lie on the imaginary axis, like this one here, it's called margin stability or neutral stability. So this one is called margin stability. And here the system is unstable because it is increasing with time. So this location is extremely important. Here, for example, if the system is on the imaginary axis, this is what you have, marginally stable. If the pole here is located here or here, the behavior will be like this. It will be increased with time. If the pole is 0 at here, when this is the question, the answer for the Sultan al-Awad, it will be constant, it will be stable. So if the pole is here, it will be here. If the pole is here, here we have this part of the pole, sigma plus j omega t, which is the real part is negative, but the imaginary part could be positive or negative. So now we care about the real part. The real part will be a decaying function, and the imaginary part will be a building function inside it. So the system will be stable or unstable, but the most important thing is we divide the system, we divide the pole, in this case, into 2 parts. The stable region, which is the left-hand side plane, and the unstable region, which is the right-hand side plane. So the right-hand side plane is a part that the system is unstable. The left-hand side plane, this is the left-hand side plane, the system is stable here, and this one, the red line, is called the marginally stable side here. The marginally stable, margin stable means عند الحافة, on the border lines. On the border lines means marginally stable. If it goes this way, it will be unstable. If it goes this way, it will be stable. So these are the pole here, because the pole is like this. And it can be also, when you take the inverse Laplace transform, you can take it like this. K1 exponential sigma 1 e to the power j omega d. This guy here, this guy is giving the rise whether the system is stable or not stable, because the j omega t will be simply a sinusoidal function. Sinusoidal function that is built inside the envelope e to the power omega t, sigma 1 t. So how to, in fact, we can solve the characteristic equation. When we solve the characteristic equation, 1 plus js h of s is equal to 0, انتهى الموضوع. We find the pole, just solve this one, solve this characteristic equation. If you find the poles are lying on the left-hand side plane, like this, or like this, the system is stable. If the poles are lying on the right-hand side plane, so the system is unstable. Nowadays, we have MATLAB, we have Mathematica, we have so many sophisticated tools that can solve this type of equation. But before, there was no such tools, and it is very complicated and time-consuming to solve this type of equation. So Routh came with a condition saying that if certain conditions are satisfied, the system is stable. If certain conditions are not satisfying, the system is not stable. One of these conditions, the necessary but insufficient conditions, are like this. He said that if all coefficients of the characteristic equation have the same sign, so the system could be stable, not 100% stable, but could be stable. If also none of the coefficient vanish, all of the coefficient polynomial should exist, it could be also stable. As you can see, it is necessary, but not sufficient. One of these, if we take an example here, if we now see this example, this is a positive coefficient, positive coefficient, positive coefficient, negative coefficient, positive, positive, positive. So since we have one negative coefficient, so the system is unstable. Directly, you have a pole. If you solve this equation with MATLAB, you will see that you have roots, especially real roots, or the real part is lying on the right-hand side plane. So it is unstable system because it has a negative sign. Now, if you see this equation, the system is not stable because of the negative sign. So another example here, if we see that we have all the power, you see we don't have the power 3. Power 3 here does not exist. معناته the system is also not stable. أخونا هذا, the Routh said all the coefficients should be positive and all the power, the coefficient of the power should not vanish. So here, since we have the term s cubed is missing, therefore the system does not satisfy the necessary condition for stability. These are the conditions. All the coefficients should be have the same sign, and none of the coefficients vanish. They should be there. This is, as you can see, necessary but not sufficient condition. Then he went and then he found another coefficient or another condition. It's necessary and sufficient. Necessary and sufficient condition is that the polynomial Hurwitz determinant dk should be positive. I'm coming on next slide to explain to you what is this polynomial. So this polynomial, if it is, if the determinant is positive, معناته the system will be stable system. The roots of the characteristic equation will lie on the left-hand side plane, and the system will be stable. If we take this one, Shabab, هنا, how to apply the test for Hurwitz criterion, the characteristic equation can be written in this form: an s to the power n, an minus 1, s to the power n minus 1, an minus 2, sn to the minus 2, a1 up to a0. So this is your characteristic equation that you obtain from your system. Now he's telling you the step one is arrange the coefficient in the above equation into two rows. Yani write here now s to the power n, s to the power n minus 1, and then s to the power n minus 2, s to the power n minus 3, and so on. Sn, the coefficient of Sn, you will do it this way. You will start an is here, an. Next will be an minus 1 is here. Next will be an minus 2 is here. Next will be an minus 3 is here. So you will go like this. an minus 1, an minus 2, an minus 3, an minus 4, an minus 5, an minus 6, an minus 6, until you end by 0. And then you form these coefficients from the characteristic equation. The other coefficient, I will show you now how we can find them, like this. So now we have this row or this characteristic equation. Now to form the coefficient of s to the power n and s to the power n minus 1, it will be like this. First of all, you go the coefficient of s to the power n is an. The coefficient of s to the power n minus 1 is an minus 1. Next, a coefficient of Sn minus 2 is An minus 2. And then the coefficient of An minus 3 will be An minus 3. Coefficient of An minus 3 will be this and this. So you form just the two powers, Sn and Sn minus 1. You form this one like this. You can just say it starts An. I will start by An as to the power n. An. And then I jump this one, and then An minus 2. And then I jump the next one, and then An minus 4, and so on. When I reach the s to the power n minus 1, it will be like this. It will be n minus 1. An minus 1 is for s minus 1. I jump I jump An minus 2, I will go to An minus 3. I jump An minus 4, I will go to An minus 5. In such a way, I have formed now the coefficient for s to the power n and s to the power n minus 1. Now, what happened for s minus 3, Sn minus 4, s to the power 0 is this one. Here now we will have Bn minus 1, Bn minus 3, Bn minus 5, Cn minus 1, Cn minus 3, Cn minus 1, until we reach Hn minus 1. How to calculate this Bn minus 1, Bn minus 3, Bn minus 5, Cn minus 1, Cn, it's this way. When we look for the next one, Bn minus 1, it will be like this, Shabab. We are looking here now, I want you to pay full attention. We are looking for this coefficient is equal to what? So this coefficient, Bn minus 1, will be this times this, yani An minus 1 multiplied by An minus 2 minus An times An minus 3 over this guy. So I will write it here. Bn, it's written here, it's written, but I will repeat it here. Bn minus 1 will be simply An minus 1 multiplied by An minus 2, okay? An minus 1 multiplied by An minus 2 minus An times An minus 3 over Bn minus 1, over An minus 1, sorry, over An minus 1. Similarly, now, how to get Bn minus 3? This is Bn minus 1. Bn minus 3, Bn minus 5, Cn minus 5, I will show them to you now in the next slide, how to do it. This one. If we do it with 6 degree, which is easier for you, so we end up by starting by s to the power 6, and then s to the power 5, because my equation is like this, s to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. Now I will form the columns of s to the power 6 and 5. So A6 will be A6, and jump next one I will have A4, and jump next one I will have A2, and jump next one I will have A0. Now I will come to A5, s to the power 5. When I come to s to the power 5, I will have the following. A5, and then jump next one, I will go to A3, and then jump next one, I will go to A1, and then 0. There is nothing, 0. Now I formed the s to the power 6 and s to the power 5 from the characteristic equation. Now how to form the rest coefficient is like this. Now here, how to form this guy, s to the power 4. This guy will be A5 times A4, this one, this times this, minus A6 times A3, minus A6 times A3 over A5 here. I will call it A. I finished with this one. I will go to the next one, this one. This one will be A5 times A2, A5 times A2, minus A6 times A1, minus A6 times A1 over A5. The last one here, this one, the B, the last one here, it will be A5 times A0, A5 times A0, minus A6 times 0 over A5. I finished the first row. I'm calling them capital A, capital B, capital C. capital A, and capital B, and capital C. Now, the next one here, the next one will be this A times A3, sorry, this A times A3, which is here, A, capital A times A3, capital A times A3, minus A5 times, I'm here. Yeah, this one, I already did it. Now I will go here. I finished with this one. Now I will go here. This will be A, capital A times A3 minus A5 times B over capital A. This one, how to calculate D? It will go from here. It will go from here. So from here, I will say D will be capital A times A1, capital A times A1, minus capital A times A1, minus A5 times E0 over A, this one. And then here, I will have A times 0 minus A5 times 0 over A, and so on. So next one will be this times this over this minus this over this one, see, and so on. So now after that, when we finish all the combination, and what I need only this first column. I need only the first column. This coefficient, the system to be stable, the coefficients here must be positive. All the coefficients must be positive. This is positive, 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 and this is positive. Now, the system to be stable, this coefficient must be positive. If any one of these is negative, I'm looking for only sabab. I'm not solving the equation. I'm looking only for the sign. If the sign is changing, if there is a negative sign, suppose here now we found this is negative. So how many poles here now? I have from here to here, sign change, from positive to negative. This is the first change. And from negative to positive, this is the second change. So I will have two sign change in the first column, and the system will be unstable because we have sign change, which is from negative to positive or from positive to negative. This is also the way how to calculate the coefficient for the previous table. We can say determinant, only the determinant of this one is here over A5. B will be calculate determinant of this coefficient between this and this and this and this here divided by B. Here, the determinant will be only between A6, A0, A5, A0, and this one. And this one here will be the determinant of this A5, AE, A5, AB, and then C, and so on. So we will do it step by step with some example here. Check whether this system is stable or not stable. We have this H of S given by this equation. Now we go directly to the characteristic equation, which is the denominator. Try to solve with the denominator. So you have S to the power 5. So we start by S to the power 5, the highest power, and then S to the power 4, S cubed, S2, S1, S to the power 0. And then we form the coefficient of the two highest power. So we started by S to the power 5. The coefficient of S to the power 5 is 1. And then I jump this one. I will go to the coefficient of S to the power 3 is 3. I jump this one and I will go to the S, which is 16. And then I jump and then go to 0. Next, I will form the S to the power 3. S to the power 3 coefficients will be like this. S to the power 4 here started by 1. And then I jump the next one, I will have 9. And then I will jump the next one, I will have 10. And then I will have 0. So I formed the array. You can do it this way, Shabab. You can say the coefficient will be equal to this. 1 for S to the power 5, and then 1 for S to the power 4, and then 3 for S to the power 3, and 9 for S to the power 3, and then 16 for S, and then 10, and then 0 and 0. So you can go either this way or this way. You can do it. Now, how to find the next coefficients will be like this. Will be here. how to find this guy? 1 times 3 minus 1 times 9 divided by 1. This will be here. 1 times 3 minus 9 times 1 divided by 1 will be minus 6. Now, how to find this? It is 1 multiplied by 10, by 16, minus 1 times 10 divided by 1. We found 6. Now here, 1 multiplied by 0 minus 1 multiplied by 0 over 1 will be 0. We found this one. This one we finished. This one we finished. This one we finished. Now, how to find the coefficient of S2? We'll start here. Minus 6 times 9 minus 1 times 6 divided by minus 6. This will give you 10. And so on. So, and so on. You will continue. Here, how to find this one? It will be minus 6 times 10, and then minus 0 times 1 divided by minus 6 will give you 10, and so on. Usually, to find the rough stability, we are interested in the first column, Shabab. This is the first column that you should concentrate on it and find the coefficient for it. The next one will be to find the coefficient here. It will be 10 multiplied by 6 minus 6 multiplied by 10 divided by 10. This will give you normally 10 multiplied by 6 minus 10 multiplied by minus 6 divided by 10. It will give you 12. And then next one here, it will be 12 multiplied by 10 minus 10 multiplied by 0 divided by 12. It will give you, this will be 0. This will be simplified by this. This will give you 10. So we finished the first column of the rough array, and we will see now that we have a sign change here from positive to negative. From positive to negative, like you see the arrow now. This is from here to here, the first sign change from positive to negative, and then the second sign change from negative to positive, and then the system is unstable. This tells you that your roots, you have two roots lying on the right-hand side plane. Two sign change. There are two poles on the right half of the S-plane, and the system is unstable. Is that right, Shabab? So you can solve, by the way, you can solve this by MATLAB. You can see it. Now we solved this one by MATLAB, or we plot it using PZMap plot in MATLAB, and we found that we have 5 poles, Shabab. The equation, since it is a 5 order, 5 poles, we have 2 poles that are lying here on the right-hand side plane, and 3 poles are lying here on the left-hand side plane. These 3 poles that are lying here on the left-hand side plane, there is no problem with them. But these 2 poles are lying here, and the real part is positive. This real part is causing the trouble and is causing the system to be unstable system because of these real parts that are lying on the right-hand side plane. واضح شباب? Now, if we go to MATLAB and solve this equation with MATLAB, no, I did not solve it with MATLAB. Just if you solve this equation, you give this equation, you can call this one P, and then with MATLAB, you give the coefficient, and then say just roots or roots of P, you will get it to have these poles here that are in MATLAB, which are given to you. -1 plus 2, -1, -1 minus 2i, and then +1 plus 2i, and then plus 2, 1, and minus 2i. So when we have these poles, especially these two, they are real, and this gives the system unstable. تفضل هاني.
بعد فضلك دكتور، بس لو ترجع السلايد اللي قبله. لا هذا اللي تو ايوه هنا. هنا بالاس 5 والاس او اس 4 واضح اللي هو هذا عباره عن كوفيشنت. بالاس 3 الى ما الاس 0 6 هذه ريبريزنت 10 12.
انتبه بس انتبه
منتبه معك يا دكتور، واضح.
تفضل
بس انا ما فهمت. لا منتبه معك يا دكتور، منتبه يا دكتور. سؤالي واضح، بس هذا اللي ريبريزنت 6 10 coefficient هذول ولا solution ولا؟
حاول تنتبه هاني. Just pay attention. So
I'm asking a question. Yeah.
How to calculate this? These are called Routh array or the determinant of the array. These coefficients are coefficient of the Routh array. How to find them? We multiply this by this, minus this by this, divided by this one. We found here -6. The second one here, we multiply this coefficient 1 by 16, minus 1 by 10 divided by 1, we find this. These are called the coefficient of the Routh array. This is called the Routh array. They represent the Routh array. Now we are interested in the first column of the Routh array. Now we are not solving anything. We are just finding the coefficient of the Routh array. If the coefficient of the Routh array, one coefficient is negative, the system is unstable. These multiplications, they show you how to find them. The steps how to find them, I'm showing you the steps how to find them. The coefficient now, this is negative. So from positive to negative, this is the first change. From negative to positive, this is the second change. We have two sign change. Two sign change means we have two rods lying on the right-hand side plane, and the system is unstable. To calculate this, these are given from the polynomial. You can, to calculate this, it's explained here. If it's not clear, I will explain it back again. فارس تفضل.
السلام عليكم دكتور.
عليكم السلام أهلين فارس.
سلو مثلا s to the power 1 the coefficient حقته مو 16 equals 0, so there will be the array will end at s to the power 1, so it will be unstable.
لا هنا we are interested هنا فارس. We are interested in the first column. We calculate the first column only, the first column. هادو they are not important بالنسبة للstability. هادو they are not important بالنسبة للstability. Try to not look at them, but هنا we need this. We need this one to calculate this, but for decision we need only this one. So how to calculate this, I will repeat. I know maybe some of you, they are not getting it, but try to concentrate with me. So how to calculate this? How to calculate S3? We take this times this, 1 multiplied by 3, minus 1 multiplied by 9 over 1. We got -6. 1 times 3 minus 9 times 1 divided by 1 is -6. انتهينا من هذا. Now next one, this one. And this one will be 1 times 16 minus 1 times 10 divided by 1. This will be 6. So this one will be 1 multiplied by 0 minus 0 times 1 divided by 0. This is not important. So for calculation, concentrate on this one. Now next one, Shabab. How to calculate? We finished with this. Now how to calculate this? This one will be -6 times 9 minus 6 times 1 divided by -6. So -6 times 9 minus 6 multiplied by 1 divided by -6 will get 10. Now how to calculate this? This one will be -6 times 10 minus 1 times 0 divided by -6 is 10. Okay, Shabab? And so on. So we found this one. We found this, and then here. How to find this? This one will be 10 times 6 minus 6 times 10 with minus here divided by 10. This will give you 12. And then this one will be 10 times 0 multiplied by -0 times 6 divided by 10. You will get 0. Last one here, this will be, we found it. Last one will be 12 times 10 minus 10 times 0 over 12 will give you 10. This is how to calculate them. Now, as you can see, now we are interested on the sign only. حتى الرقم في حد ذاته, we don't care about it. حتى الرقم, now we are interested in the sign. If there is a sign change, this means that the system is unstable. So from here to here, there is one sign change. The first sign. From here to here, the second sign change. So the system is unstable because we have two sign change from here to from positive to for which the system will be stable. Of course, you will go and calculate the transfer function and calculate the characteristic equation. There is no need, Shabab, to calculate the transfer function C of S over R of S, because we already know that the characteristic equation is simply 1 plus GS H of S. 1 plus GS H of S equal to 0. So you calculate directly the characteristic equation, which is 1 plus K S times S plus 1, S plus 2 is equal to 0. Here, when you calculate this one, you end up by having this equation or this equation. Now you get the characteristic equation in terms of S cubed plus 3S squared plus 2S plus K is equal to 0. You form the Routh array, S cubed will be 1. You jump next one will be 2S, 2. And then you jump next one, it will be 0. Now S squared, you have 3. And then you jump next one, you jump the 2, you will have K. So here you will have 0. Now you will form the Routh array starting from S to the power 1 and S to the power 0. So here, this will be 3 times 2 minus K times 1 divided by 3. 2 times 3 minus K divided by 3 will give you 6 minus K over 3. So here, how to get this one? This one will be 6 minus K over 3 multiplied by K minus 3 multiplied by 0 by 6 minus K over 3. So you simply, this will be 0. You simplify 6 minus K over 3, 6 minus K over 3, it will be K. So now you decide, the decision you should take is the column, the first column or the elements of the first column must be positive. This guy is positive, there is no problem with it. This guy is positive, so we need to have this guy positive and we need to have this guy positive. So the first is K S to the power 0. S to the power 0 give you the condition that K must be positive. This K must be positive. And the second case, S to the power 1, S to the power 1 should give you this parameter, 6 minus K over 3 positive. 6 minus K positive معناته K should be less than 6. يعني في الحقيقة هنا we should have K positive and at the same time K is less than 6. The two conditions must be satisfied. The two conditions must be satisfied at the same time. So the first condition, K must be positive from here to here. From here to here, to infinity. And the second condition is K must be less than 6. Less than 6. So here. So inside this interval, I'm inside this interval, this one. This is the condition of the system to be stable. It should be between K greater than 0 and less than 6. This is the condition. But what will happen, Shabab? This is the condition. Is this okay, Shabab? Inside هنا the interval K must be less than 6 and greater than 0 must be stable. Any question for this? The two conditions must be satisfied at the same time. But what will happen, Shabab, when K is equal to 0 or K is equal to 6? When K is equal to 0 or when K is equal to 6, this is what we have. We substitute in the characteristic equation K is equal to 0. You know, we substitute K is equal to 0. We end up by solving this equation. S cubed plus 3S squared plus 2S plus 0 is equal to 0. Or you can take S common here. You will end is when k is equal to 6, because we have two conditions here. We have k is equal to 0 and k is equal to 6. When k is equal to 6, we substitute k from here equal to 6, and we solve this equation, s cubed plus 3s squared plus 2s plus 6 is equal to 0. So s squared, you can take s plus 3 common, and you solve for this equation. If you solve for this equation, you will get s is equal to minus 3. And this equation will give you s is equal plus or minus j square root of 2. S is equal plus or minus square root of j is here. So this one will give you the system marginally stable, then your poles will be located on the imaginary axis, j minus j square root of 2. So here now the system, the frequency of oscillation will be omega is equal to square root of 2 radian per second. At these two values, the system will be marginally stable, and the other pole is located here as minus 3. Minus 3 will be stable. واضح شباب, this is when we have a condition for stability, يعني for which value of k the system is stable. Now we care about the stability because stability will give you a stable system. If your system is not stable, you are afraid that